The second speaker of the session would then be Rajes Ghosh. Rajesh, can you share your screen, please?
Yes, thank you. The slides are visible, right?
Yes. So your talk is for 15 minutes. I'll give you a reminder at 12 minutes, and the remaining 3 minutes will be for questions.
Okay, thank you.
Okay.
Yeah.
Please start.
Okay. So first of all, I would like to thank the organizers and organizing committee for giving me this opportunity to present our work here. I will be talking about causality constant in quadratic gravity, and this talk will be based upon our recent work, which I have mentioned here. And after I will give the motivation of our talk. Then I will move on to developing some tools that we will be requiring for this talk, namely the concept of Shapiro time shift and the shockwave in various gravity theories. And finally, I will conclude with the result that we have got in the context of quadratic gravity related to causality constant. All right, so, let's move on to motivation. And let's start with something which everyone knows, namely the Einstein-Hilbert action. And what we have, I have written here. And by varying this action, we get Einstein's field equation. This action is invariant, as you know, that by general coordinate transformation, x mu goes to x mu plus xi mu, which is also known as diffeomorphism invariance. And if we also added this energy moment, the matter Lagrangian here, by this diffeomorphism invariance, it is very easy to show that energy momentum is locally conserved. Okay, but if this diffeomorphism invariance is only guiding principle for writing down an action, so we can add various other terms to this action. For example, I can add in quadratic order like R square, RAB, RABCD, RABCD. So I have mentioned some of the terms, some of the particular theories that we'll be requiring in this talk, like quadratic gravity, where I have added R square and RAB with this dimension full coefficient alpha and beta. Also the well-known Gauss-bounded gravity by this combination of terms. But this is not enough. We can also write down or add terms like quadratic and in cubic and quanti-quadrat terms, and so on. So it is clear that we have an infinite number of theories to consider and to check with experiments. But we can ask the question: does all the diffeomorphism invariance are healthy? Healthy in the sense that are all the diffeomorphism invariance theory are theoretically consistent? For example, in 2016 paper, Kamano et al. Has shown that the Gauss-bounded gravity, this well-known theory, has some problem with causality. And I will discuss in more details what do I mean by this problem with causality. But the message is that there is some problem with Shapiro time advancement, and this leads to causality violation, like you can make like a time machine or something like that. Okay, this is the message from this paper, and it can also be shown by generalization of their work that it is true for also Lovelock-Lagrange gravity, any higher order theory also, that you have this causality constant. Now, a natural question asked at this point is that can we construct a theory, or even better, can we construct a general class of theory which does not possess this kind of causality issue? And that is our motivation for considering such model. And the answer to this question, that can we consider can we construct such model which don't possess this causality issue, is yes. That the quadratic gravity, for example, does not possess such issue. And we also find out that for a general class of theory, there is no such problem. And I also emphasize here that we are not considering quadratic gravity as a viable theory of gravity. It may be or it may not be, but for that we have to consider other theoretical issues like positive mass theorem, ghost mode, tachyonic mode, etc., etc. But what we are emphasizing in our work is that it is the simplest non-GR model which has this nice property that it does not suffer from causality issue. Okay. And this consistency criteria and this by which I mean this causality constant may help us in future in final classification of all classical theories of gravity. And if we can classify all the consistent theory of gravity, then by studying a particular theory of gravity, we can make some general claim about the whole lot of theory in a particular classification. Okay, so that is the hope. Okay, so let's move on to the review of Shapiro time shift and the shock wave, which we'll be requiring in this talk. And the concept of Shapiro time shift can be illustrated very easily by this cartoon. And now here we are considering a light beam which is propagating back and forth for, let's say, Earth to Venus. And here we will consider only the gravitational influence by sun, and we neglect the motion and the gravity of Earth and Venus. Okay, in the course of this propagation of light. And in the absence of sun, it is clear that we can use this Pythagoras theorem to calculate what will be the time taken by this light beam to complete this back and forth journey. So it is given by here, where R0 is the closest approach of the light beam to the sun. But in the presence of sun, we can characterize the outside space-time by the Schwarzschild metric. And in that case, in the modified geometry, the Pythagoras theorem will be modified, and we can also calculate by analyzing the null geodesic equation what is that light travel time. And it turns out that for this case, the Schwarzschild time, okay, for the Schwarzschild case, the time light propagation time is greater than the Minkowski time. So we can define a useful quantity for this kind of experiment, which is called the Shapiro time shift. That is, I will denote by T Shapiro, which is just the Schwarzschild time. In this case, is the Schwarzschild time, or in general case, any Carr space time minus the Minkowski time. And this quantity can both be positive or negative. For our consideration that we have considered this cartoon thing. For this, it is a delay. That means that Ts is greater than Tm, and this type T Shapiro is positive. But in general, it can be negative also. For example, if we consider time-like propagation between two Schwarzschild black holes, it can be shown that T Shapiro is negative for certain velocity. Okay, and note that in general, T Shapiro negative does not, or Shapiro time advancement is not acausal. For example, even for this time-like propagation, it can be shown that Shapiro time advancement is possible. But what is acausal really is that when Ts is less than 0. Okay, that means you come back here before we start. You come back here by completing the journey before even you have started. Okay, all right. And we want to calculate for this talk the Shapiro time advancements or delay, whatever it is, in the shock wave background. So let's consider the shock wave. And what is shock wave? The shock wave is a special kind of solution of Einstein field equation with the energy momentum tensor I have written here. It is sourced by a particle which is moving very fast along a particular direction, let's say along v direction, with momentum pu. Okay, the stress energy tensor is fixed on the geodesic on the trajectory of the particle, and is given here. And if you use this stress energy tensor and solve the Einstein equation, you will get this kind of solution, where H0 is given by this F0 r, which I will call the profile function, times delta of u, where F0 r is given by this. So I have written this quantity for d greater than 4. Okay. Now here r is the distance from the UV plane, or it is the, you can also call it transverse distance. If your the screen of your laptop is the UV plane, it is the transverse distance from that plane. Okay. And please note that because of the delta u here, it is clear even from the metric that the space-time is everywhere flat except for the u equal to 0 plane. And you can re-verify it by considering the curvature, and it will be proportional to delta u. So now let's consider a particle which is moving in this background, test particle, and it crosses the shock wave with impact parameter, let's say r equal to b. So what will happen to this test particle? Okay, and it is very easy to show that the test particle will suffer a time delay given by this delta b, which is f of b, that is the profile function evaluated at r equal to b, and that is positive. Now the easiest way to show that this is really the case is to consider, because of this delta u here, you can clearly, sorry, see that I can omit this delta u, this part here, by a coordinate transformation from v to v nu, let's say, by this coordinate transformation, then the geodesic at r equal to b will be continuous. That means that in the old coordinate or in the v coordinate, it suffers a time delay, which is given by delta v equal to f of b. Okay, so that is given by this Heaviside theta function, which is clear from here. And this delay is with respect to the fastest mode of propagation along the boundary. And boundary, by boundary I means here for b tends to infinity. Okay, and for b tends to infinity, it is clear that f of b is 0, that this time delay is 0. So with respect to which I am measuring this time delay here. Okay, so we can also do the calculation for, let's say, a scalar mode or a graviton mode propagating in this background. But for the constant time, I will not go into much details about that. But I have just write down 1 or 2 equations to show that if I do the calculation similarly for the scalar wave, which is propagating in this background, when it crosses the shock wave, it also suffers a Shapiro time delay. Okay, you see that when it enters the shock, it is at 0 minus, u equal to 0 minus and v minus, let's say, delta v. And when it's come out of the shock, it is at u equal to 0 plus and v. So there is a Shapiro time delay here. Okay, but the interesting fact here in GR, you always the mode of propagation, even if it is scalar or it does not matter, or the metric propagation, metric perturbation, it always suffers a Shapiro time delay. But the things get interesting if we consider the same kind of situation in Gauss-Bonnet gravity. The Gauss-Bonnet gravity, like
Rajesh, sorry to
yes.
interrupt. You have 2 minutes left.
Oh, sorry. Yes, I will consider. For the shock wave in Gauss-Bonnet gravity, it is very easy to show that because of this delta I, delta k, the transverse derivative on the profile function, the time delay will depend on the polarization mode. And then you cannot, for any choice of polarization, there will be always the Shapiro time delay. It can be advancement also. There are always some polarization. It will be advancement. So the only way, so that means the advancement means that it is the theory is acausal, and you can also make a time machine out of it. Okay, so but I will not go into details of that. The only way to make the theory causal is to put this lambda to be 0. Okay, then that there is no Shapiro time advancement, and your theory will be causal. So that is exactly the Gauss-Bonnet, the Einstein gravity. Okay, if you put this lambda term with non-zero lambda, so then your theory is acausal. Okay, so but it turns out the shock wave in there is a exact shock wave in quadratic gravity, and which is given by this equation here. So this is the profile function, and it turns out in a shock wave if you do the similar kind of calculation in this shock wave background in quadratic gravity, okay, where the perturbation equation I have written here, it can be shown that it is always a delay. Okay, it is never an advancement. So that means the causality is respected in quadratic gravity. And in fact, you can also generalize our result in some modified gravity. But here, but because of this factorized form here, that delta v in quadratic gravity is delta v gr times this extra term here. So it may give you a doubt that maybe we can do a field definition in GR to get this result. So then our result will not be a new one, but it is not true. As you can see that there is exact a field definition which will map the shock wave solution of quadratic gravity to that of GR, but that field definition will not map the time delay of GR to that of the quadratic gravity. Okay, so this field definition trick will not work here. Okay, so the result is really new, and we can generalize our result to higher curvature gravity also, for which the field equation has this structure, the perturbation equation. And for this kind of equation also, for any n, for example, there will be n equal to 2 for this kind of gravity. So there is no problem. You can show that also. Okay, so here is some takeaways that this causality constant is really a very strong constant to rule out some of the theories, higher curvature theories of gravity. But some other theories of gravity are causality constant free, and quadratic gravity is an example of that. and it is and by field definition you cannot map the delta V of the quadratic gravity to that of GR. And analyzing some this theoretical consistency may help us in future in classifying all gravitational theories. Okay, thank you. So I'll be happy to take any questions.
Thank you, Rajesh. Are there any questions for Rajesh?
Yes, one question, Rajesh.
Yes, I'm sorry.
So Rajesh, this second point that you mentioned, ghost and tachyons.
Yes.
Like suppose I rule out the quadratic gravity on this ground.
Yes.
Are there any models left with 4 derivatives which
Yes, so that's what our generalization is. For example, you can consider this kind of gravity, but what I will say is that, for example, in quadratic gravity there are tachyonic mode, but you can always go to some subspace of the theory given by, for example, let me go back here. So there is actually no constant assumption here, that you can always go to a subspace of the theory where beta is less than 0 and d equal to 4. There is also a constant on alpha. Let's say 3 alpha plus beta is greater than equal to 0, where the theory is tachyon free. Okay, and even for the ghost term, okay, it turns out that if you put beta equal to 0, the theory is ghost free. But even that is also not required for this kind of analysis, because ghost is really, it is like your perturbative assumption. But if you do any kind of non-perturbative analysis, that is really don't know. We don't know that what is the stability. For example, there is even positive mass theorem that is true in quadratic gravity. So that means the vacuum is stable. Okay. So by only considering tachyonic and ghost mode, I don't think that we can rule out this theory. Okay, we have to consider much more sophisticated and other also theoretical consistency.
Okay, thanks.
Are there any other questions for Rajesh? If not, let's thank Rajesh,
Okay.
and let's move on.